there, and welcome back to the series on elementary statistics and probability. In this video, we're going to continue our discussion of some of the basic principles that you need to understand in order to study statistics. And in this video in particular, we're going to be focusing on a particular metric that you can use to describe samples or populations, and those are called measures of central tendency. So it's useful to give a definition, whether how good of it is at describing this topic is another story. But the general definition for a measure of central tendency is just a metric that describes a set in terms of its central position. Of course, then one may ask, well, how do you define central position? Because that term could be, for example, ambiguous, not really clear, doesn't really give any extra information. It could be very vague, that could be viewed as a synonym for ambiguous, or it could even be misleading um, based on your idea of what it means to be central or in the center. For example, it could represent the average. It could represent the direct middle, for example, the median of a data set. So in this video, we're going to look at several measures of central tendency and discuss a couple pros and cons for each of them, and then you can decide maybe which measure of central tendency you may want to use for your particular study. So let's introduce the very first one, and this is going to be probably the easiest to calculate, and that is going to be the mid-range. So the mid-range. So let's just explain what the mid-range is in terms of an example. So let's consider the set S defined by the numbers 3, 7, 16, 22, and 41. So the mid-range for a particular set S, which I'm going to just denote as mid-range parentheses S, is defined to be equal to half of the sum of the maximum element of S, so the maximum of S, plus the minimum of S. So in this particular example, the maximum element of S is going to be 41. So it's going to be 1/2 of 41 plus the minimal element is going to be 3. So that's going to be equal to 41 plus 3, that's going to be 44 divided by 2. So this is going to be equal to 21. So this is going to be the mid-range of our data set. Now, of course, it's very easy to compute, no doubt about that, but there are a couple downsides to the mid-range. For example, let's assume I have another set T that's practically the same exact thing, say 3, 7, 16, 22, 41, and I don't know, 100 or 1000 and I don't know, 3. So in this particular example, the mid-range of T is going to be 1003 plus 3 divided by 2, so that's going to be 1006 all over 2, so that's going to be 503, right? So notice that I've introduced one single number, in particular 1003, to the original set S, and notice how much my mid-range has changed. It's practically changed dramatically, even though I have introduced only one single element. And also, it's important to note that it doesn't really matter what the interior values of the set is, because the mid-range doesn't consider those values. So pro, it's very easy to calculate. A couple downsides to the mid-range, it only focuses on the maximum and minimum, and another downside is that it is extremely affected by what we call outliers. So outliers are values that are extremely different from one or all of the other values. Most of the time people consider all of the values. Of course, different is a subjective because we have to define what we mean by how far a number has to be from the rest of the data set in order to be considered an outlier. Once we talk about a few measures of variation, we'll give a more formal way to identify elements as outliers or not outliers. But at least this gives us something to think about for the time being. So that's the mid-range. What is another measure of central tendency that isn't too hard to calculate? That would be the mode. So the mode is the most frequent. So it's the most frequent data element in a set. So again, it's easy to describe this in terms of a particular example. Suppose I have 3, 4, 7, 7, 8, 8, 9, 9, 9, 10, 10, 11, and 13. So notice here, 9 repeats 3 times, and all of the other elements either repeat twice or only one time. So we see 7 and 8 and 10 all repeat twice, and 3, 4, 11, and 13 only repeat once. So we may want to consider looking at the frequencies of these data values. So for example, the frequency of 3 is equal to 1, the frequency of 4 is equal to 1, the frequency of 7 is equal to 2, the frequency of 8 is equal to 2, the frequency of 9 is equal to 3, the frequency of 10 is equal to 2, and you probably get the point, right? So when you're considering the mode, you need to find the one with the largest frequency, and that's going to correspond to the mode. So here we see that the mode of this set S is equal to 9. Now again, similar to the mid-range, the mode only focuses on one particular element, in particular the most frequent element. If I were to introduce several other numbers, I can even introduce some numbers that are really different. So I could add, say, 14, 15, 15, 16, and 1000. And notice that the mode still would remain to be equal to 9. So it doesn't consider all of the values, it only considers the most frequent one. And it doesn't really change if an outlier is introduced, so that's technically a good thing. But it's not really well representative of the data sets. Um, and it doesn't even have to be in the middle. For example, the most frequent element could be 3, and all of the other elements greater than it could have a frequency of 1. So the mode usually isn't used for as a measure of central tendency, but it can be used if you have good reason to do it. Also, if you have, for example, let's assume that 8 repeats 3 times and 9 repeats 3 times, and those are the two elements that repeat the most. Sometimes we would refer to that as a bimodal set, and you could even consider like a trimodal or a quadmodal type of distribution. But usually those have no meaning unless you have a really large amount of data points. So for example, if we look at the frequencies for these values, right? So let's assume that our frequencies sort of have this type of shape, right? So clearly, whichever one has the highest frequency value, that's going to be our mode, right? But what about our frequency distribution and it looks like that, right? So if we sort of draw horizontal lines here, this element here isn't the highest element, so of course definitely this would be a mode. But if you have some sort of position assigned to all of your values, then you might want to consider the mode with respect to its local neighbors. So for example, if we look at this particular valley, we can partition this set into, for example, a left and a right-hand side. And this would be the mode for the right-hand side, and this would be the mode of the left-hand side. So there are some certain scenarios where you may want to partition your data set into 2 or more categories. And then you might have multiple modes, even if they do not have the same and equal frequency for the data set. But those go into very particular examples, but as long as you're aware of these special cases, you can definitely do a lot more with them. But again, it's not really well representative of the entire data set. It pretty much ignores all of these values here, and if we only define the greatest, then it pretty much ignores that value as well. So what's another measure of central tendency that we could probably use to have some sort of idea of the center of the distribution? And probably the next easiest thing to use would be the median. And the median is actually a very crowd favorite in terms of measures of central tendency, but it requires one thing. It requires your data set to be ranked. And when I say ranked, I just mean ordered from least to greatest. Ordered from least to greatest. So you can't have 3, 2, 1 as your data set. You have to have 1, 2, and 3. And the median actually has 2 variations on how you're going to calculate it, and I'm going to give you an example for both. So you have case 1. That's if your cardinality of your set or the size of your set is odd. That's probably the easiest case. And case 2 is if the size of your set is even. So let's look at an example where the cardinality of a particular set is odd and discuss how we're going to find the median of that particular data set. So we have A, so this is going to be our set. This is going to consist of the values 7, 12, 15, 21, 55. So we see that this set is definitely ordered from least to greatest, so it is a ranked set. And the median is going to be the middle rank value of the set, right? So this is rank 1, rank 2, rank 3, rank 4, and rank 5. And the middle rank from 1 to 5 is going to be this element 3. You could actually find this digit or this index by averaging the middle and the maximum elements. So 1 plus 5 is going to give you 6, divided by 2 is going to be 3. So this element here is what we call the median of the data set values, right? And if the data set is odd, that means you're going to have the equal amount of elements to the left greater, or to the left less, and to the right greater than that particular element, or greater than or equal to if you have some repetition going on there. Now, if you have an even number of data values, for example, consider the set B, 3, 8, 11, 15, 17, and 18, again, you're going to require that the set be ordered from least to greatest. And what you're going to do is you're going to look at the middle two values here. So again, this is going to be rank 1, rank 2, rank 3, rank 4, 5, and 6. Now, in order to find the minimal index very quickly, if you have a very large set, so how can we get this number 3? So what we can do is we can take the maximal rank, or the cardinality of a set 6, and divide it by 2, and that's actually always going to give you this first element. And then the next element that you're going to consider is that index plus 1. So we're going to consider these two values and then take the average of those particular values. So the median of an even cardinality set is always not necessarily in the set, right? Because as we can see, 11 plus 15 is going to be equal to 26, and 26 divided by 2 is 13, which is not in the set, but this is what we typically refer to as the median of this particular set. So the first one here, the median is equal to 15, and the other one, the median is equal to 13, right? So first, figure out is it ordered or is it not, and if it's not, order it from least to greatest. Then determine if it's odd or even, and then you can figure out how you can go about finding your median. Now, does it consider all of the values? No, actually it doesn't consider any values at all. But it does require that all of the values be ordered. So it sort of indirectly considers the values because it considers their comparison to one another in terms of least to greatest. So that's an interesting thing to note. It doesn't really consider the values, but it considers the rank of all of the values. So that's a bit interesting. Now, what about outliers? Does it really change a lot in regards to outliers? Well, we can consider a basic set, for example. So S is equal to 1, 2, 3, 4, 5, 6, and 7, right? So if this is our data set, then our median is going to be equal to 4. And let's assume we add a new value into this set. So let's union this with the set, I don't know, 1 with a bunch of zeros, right? So that's definitely an outlier. It's really different than these single digit numbers. So what is our new median going to be equal to? So now we have an even number of data points. So we have those 4 there, we have these 4 there. So the median for this is going to be 4.5. So before the median was 4, we've introduced this. What number is this? Is going to be 10 million. We've introduced 10 million into this data set, and notice that the median has only changed by 0.5 units. So if an outlier is introduced, the median is not going to drastically change that much. So this is one of the reasons why the median is a commonly used measure of central tendency. But there are other measures of central tendency that we have yet to discuss. So let's get into them now. All right, so the next measure of central tendency that we're going to look into is going to be referred to as the geometric mean. If you've heard the word mean before in terms of calculations, you've most likely been working with the arithmetic mean or the average of a data set. But there's actually at least two different types of means that are oftenly used, the arithmetic mean and the geometric mean. So let's just talk about this one first and briefly discuss when you may want to use one over the other. But there's one requirement that we need, at least for the time being, for the geometric mean, and that is that all elements, all the data values in our set, must be positive. So they can't be equal to 0 or negative numbers. Okay, so you can't have a -3, 0, -26.2 values in your data set. So the geometric mean of our sample, I'm going to represent it by G for our sample to distinguish our population parameter calculation notation, is going to be equal to the nth root of the product of all of the values. So k is equal to 1 to n xk, where xk are elements of our data set S, and n is going to be the size of our sample. Right? And if you're not familiar with this notation here, that just means multiply all the values together in your set. So it's fancy pre-calculus notation. So to illustrate this with an example, so let's assume our set is equal to 3, 7, and 10. So if this is a sample, then the geometric mean is going to be equal to, so since we have 3 elements in our set, that's going to be the cube root of the product of our elements. So that's going to be 3, 7, and 10. So that's going to be the cube root, let's see, what's that? 7 times 3 is 21, times 10 is going to be 210. And if we use our calculators or whatever methods, that's going to be approximately equal to 5.94. That's going to be the geometric mean of our sample. And what if we want to find the geometric mean of a population? Would that be any different? And the answer is no. But you would have to most likely use a different notation because usually statistics and parameters represent totally different ideas, even though one is an estimate of the other. So we're going to be using the Greek letter gamma. So this is going to be gamma to represent the geometric mean of a population. Okay, so this is going to be a parameter for a population. So population. And this is going to be defined very similarly. It's going to be the capital Nth root of the product from k is equal to 1 to capital N of xk. Here xk are elements belonging to our population, all of them, and capital N is the size of our population. Right? So it's practically the same exact thing, similar to the calculations of arithmetic means for samples and populations. Now, when would you use a geometric mean versus an arithmetic mean? Usually when you're dealing with multiplicative processes. For example, if your population's increasing by percentages, and that's how you're measuring the change in population. So for example, if it increases by 2%, if it decreases by 6%, if it increases by 10%, and then it increases by 2.7%, and you want to find the average or the mean percentage change across the past 4 years, a geometric mean is going to be a little bit more informative versus an arithmetic mean. And there's a long reason behind that, but I'm not going to get into it now. But usually when you're dealing with multiplicative processes, you're going to be dealing with a geometric mean. And when you're dealing with additive or subtractive processes, we're going to be working with the arithmetic mean, which is probably the most familiar to you. And that's usually sometimes just referred to as the mean or the average. So again, for the sample, we're going to be using x bar to represent the sample mean, and that's going to be equal to the sum from k is equal to 1 to n of all of our values divided by our sample size. Again, x, that should be k. So xk are elements belonging to our sample, so x1, x2 down to x little n. And little n is just the size of our sample. So remember that fancy sigma notation just means add up all of our values together and then divide by our sample size. And similarly, mu is going to represent our population mean. So that's going to refer to our population mean. I guess those should be in the same color to keep everything uniform. right? So that's going to correspond to our sample, and that's our population mean. And it's calculated in a very similar way. It says the sum of all of our population values, xk, divided by our population size m, where xk belongs to our population and capital N is our population size. So the calculations of sample and population, geometric and arithmetic mean, is practically the same, except one you're dividing by the sample size or taking the sample size root of the product, and the other you're doing the population size as your calculation. Keep in mind, x bar and g are statistics, and mu and gamma are parameters. So let's just do a quick example on how you would calculate the sample mean. So for example, s, let's assume s is equal to 5, 7, 3, 4, 10, and 7. So if this is the case, then the sample mean of s is going to be equal to, and if you're only dealing with one set, you don't have to subscript your sample means or your geometric means or anything, because there's no confusion that could possibly happen, but you can always subscript if you're not sure. And that's just going to be 5 plus 7 plus 3 plus 4 plus 10 plus 7. All over we have 6 values, so that's going to be equal to 36 over 6, which is just equal to 6 as we know. So that's going to be your sample mean, and the population mean calculation is practically the same exact thing, right? And keep in mind, x bar is an approximation for mu, right? So let's just summarize that from the last time. So x bar is an estimate for mu, and g is an estimate for gamma, right? So one is a statistic, and the other is a parameter. Statistics are calculations on samples, and parameters are calculations on populations. Right. There's also the weighted mean. That's also another type of measure of central tendency that you may encounter, and that's usually the weighted arithmetic mean or the weighted average of a set of data points. For example, if you want to do the weighted mean of a data set, let's assume S is equal to 3 and 10, and you want to give different weights for these values. So let's assume we want to add a weight of 20% to that one and a weight of 80% to that one. So usually the sum of these weights must always be equal to 1. And then the weighted average, I'm going to just call it W. I'm not going to introduce more notations here. That's just going to be equal to 0.2 of 3 plus 0.8 of 10, and then we're going to just divide that by 2, and that gives you the weighted average of that data set. But that's not usually considered, at least for now, but at least you're sort of aware of the idea that weighted means and weighted medians could exist, is practically all that you need. Now, of course, we've described several different measures of central tendency: the mid-range, the mode, the median, the geometric mean, the arithmetic mean, weighted averages. You could even do hybrid forms if you want to. For example, you can create a measure of central tendency on your own. For example, you can call it star, and you can say, okay, this is going to be the weighted mean of the arithmetic mean, the geometric mean, and the median, right? So this star measure of central tendency can be equal to, so remember, the median is not affected by outliers, so maybe we want to weigh the median of a data set a little bit more heavily. The arithmetic mean, is slightly skewed by outliers, so we can sort of do like a 20% distribution there. And for example, we can do 0.1 of the geometric mean G of a particular data set S if we really want to. And we can divide by 3 if we really want to, or we can divide by some other number if it has some relevance to us, or you can just treat that as your measure of central tendency, right? Your star measure of central tendency. But there's lots of things that you can do for this, but you have to have reasons for why you're choosing these particular measures of central tendency for your study. And that's, of course, a more advanced discussion. But for now, let's just worry about how to calculate them, some of the pros and cons between them, some of the times that you may want to use one over the other, and also how outliers may influence each of these measures. So, of course, remember the main goal of statistics is to study a population by looking at its calculations and properties of all of the samples that we may be able to collect from that population, and then use metrics to make those inferences about the populations. So this time we've only focused on measures of central tendency. In the upcoming discussions, we're going to discuss measures of position and also measures of variation that are commonly used, and those will tell us other things about the populations and samples that measures of central tendencies do not tell us. So I look forward to seeing you there, and I hope you have a good day. Take care.